Hello everyone. In this video, we present our work on efficient verification of neural networks against LVM-based specifications. Broadly, the work combines generative modeling and formal verification to give deterministic guarantees on network performance against a continuous set of diverse variations prevalent in a dataset. This has been done before, and the focus of this work is on A. Improved effectiveness. That is, verification outcomes should be independent to decoders' reconstruction capability, and B. Improved verification efficiency and general applicability. The heart of the approach is this multi-hit pipeline, where this part is the original network to verify, and this part a generative model. The encoding head of the generative model is invertible and maps the specification defined in latent space back to the network feature set, so the network can be verified for an output property with minimal reconstruction overhead. This approach, while improving verification feasibility, requires greater training effort and large and finely annotated datasets. With this overview, we now discuss each aspect of the work in greater detail. The motivation. Deployment of neural networks in safety-critical applications requires assurance on their robustness. A deterministic way of establishing local robustness is through formal verification. Given a network and desired input-output constraint set or specification, formal verification establishes whether the network satisfies the constraints or not. If not, it returns the failing case or the counterexample. Typically in neural network verification, the specification is a continuous set around the input, and verification tools allow one to pass this entire set through the network in a single forward pass and establish whether the network output for the entire set is as desired or not. The computational expense of verification can scale exponentially with the input and network size, so when a verification problem fails to be solved, then the satisfiability is neither proved nor disproved. Our work mainly contributes to the specification design element of verification. Now, most input specification for images capture the pixel-wise norm-bounded variations or the parameterized geometric and bias field variations as shown. But how do we capture the diverse, often arbitrary variations that are difficult to define mathematically, like the semantic changes in objects, spatial or pose changes, occlusions, etc.? A possibility is to use generative models that are routinely used to learn and encode these variations in a lower dimensional space. Existing works like that of Meerman et al. And Katz et al. Already add verification to this setup. So the encoder is used to define the verification specification in the latent space. A decoder is prepended to the network to be verified, and the combination of decoder and original network is then verified. However, we identified three weaknesses of this decoder prepending approach to network validation. 1. The input specification can be loose or incomplete. That is, it can capture more or less inputs than the one you want to verify the network for. Second, the network is verified against reconstructions of the decoder. If the decoder is unable to generate desired variations, then verification may incorrectly suggest that the network is invariant to those variations, when in fact it is just not tested against them. Third is the computational cost and approximation errors, which are now accumulated over more activation layers. Now it is primarily to alleviate the last two limitations that we propose our approach. Again, very quickly, in our approach, the network to be verified is split into a feature detection part and the task head. An LVM is built by adding an invertible encoding head to the feature detection network. The specification is defined in the output space of the invertible encoding head, which it maps directly back to the network feature set without having to pass it through the decoder and back through the network. Therefore, the verification backend can just verify the inverse of the encoding head and the task head. The dimensionality of the latent space is the dimensionality of the network output, which is typically always less than the input dimensionality, since the initial layers of most networks are downsampling ones. The decoder here is only used for LVM training and for counterexample generation. With this, we can now analyze this approach in light of the limitations discussed for the existing approach. First, in our approach, the network is verified for the feature set defined by the encodings of the original images rather than reconstructions. Therefore, the network is tested against at least the original images that form the basis of the specification. Then, the verification path is shorter. Therefore, in experiments, we find that for the same verification backend, more verification queries are solved with a non-trivial, that is, with a robust or non-robust outcome, and there are negligible undecided outcomes compared to the existing approach. Then, the approach gives flexibility on where the network is split, which is useful when the verification backend doesn't support or scale to the entire network. One can also use a deeper decoder to get sharper counterexample generation without hurting verification. With this analysis, we now discuss the applications of the approach, which in turn depend on the specification definitions. In our work, we propose 3 robust specifications: segment, access, and region. And the kind of variations each captures can be seen in the reconstructions here. The segment specification is a path between the encodings of any 2 inputs, which should have the same network prediction. The access specification is a set along a conditional axis that is trained to capture a specific task orthogonal aspect, such as beard and eyeglasses and gender classification or pose change. Region specification is a norm, ball, and latent space that captures the local variations most commonly occurring in the dataset. Using these specifications, we verify for robustness and object classification against planar, spatial, and semantic changes for 5 datasets as shown, and 3 deep networks of different architectures, that is convolutional, ResNet, and MobileNet. For segment and region specifications, the typical VAE and GAN training is enough. For access specifications, we need conditional training. We do conditional training in a supervised manner using cross-entropy loss or as a graphics code depending on the attribute type. We can validate its success using manifold visualization and directed reconstructions. So for instance, all images here are generated from a single image per dataset, as the encoding is perturbed in the conditioned axis with the non-conditioned axis being fixed, and vice versa. These qualitative results agree with the verification results, which show that the conditional axis can be verified, especially for lower dimensional manifolds, for much larger extents than the non-conditioned axis. Also, a quantitative way to validate the specification design is using presented metrics. Now for segment specifications, we want the encoding path to capture the semantic interpolation between 2 inputs. So, we measure the distance of the encodings of an image pair interpolation to the segments joining those image pair encodings. This can be used both for specification validation and design. For access specifications, we take subsets of dataset varying in a specific aspect and compute the ratio of the correct to the highest incorrect conditional axis capturing that particular aspect. Finally, when the outcome is non-robust, the verification backend returns a latent space counterexample, which is mapped to the data space by the decoder. However, since the decoder is not the inverse of the encoder, this image space counterexample may not result in network misclassification. For such cases, we do a local gradient-based search around the latent space counterexample, and it often results in a valid image space counterexample. These are all slightly hazy, but semantically meaningful as per the verification query and network task. To summarize, in this work, we analyze and compare the existing and proposed approach for verification against semantic variations. We formalize the design of latent space specifications and their validation. We demonstrate the approach for real-world applications, and the challenges with the proposed approach include its enhanced requirements in terms of proposed pipelines training and dataset quality, as elaborated in these points and in the paper. Thank you for listening. The implementation and demos have been made available online for you to use and play with. So, have fun. Thank you.